All right, given that the divergence measured the flux density of a vector field at a point, we're now going to look at the physical interpretation of the curl of a three-dimensional vector field. So here's the definition of the curl. And the first thing to highlight is that the k component is what we define to be the two-dimensional curl of a vector field in the xy plane, right? So if I have a vector field whose I component is P and whose J component is Q, and P and Q depend only on X and Y, right? Because it's describing a vector field just in the XY plane. Well, I can extend that vector field into three dimensions by just treating the K component R as constant 0. And then again, P and Q are just dependent on X and Y, so they're totally independent of Z. Okay, so notice that if I took the three-dimensional curl of such a vector field, the I component would be 0 because R is constant 0 and Q doesn't depend on Z, so this derivative here is 0. And the J component's 0 as well because R is 0 and P doesn't depend on Z, so that's 0. So in that case, the curl has its direction as K, and that makes sense, right? Here, if I'm thinking about a vector field swirling around in the xy plane, and the curl's describing rotation of that field, we're really describing rotation about this axis determined by the vector k. And the amount of rotation is being measured by this quantity right here, partial q, partial x minus partial p, partial y, right? It's just being measured by what we defined to be the two-dimensional curl. Okay, so now more generally, if I have a three-dimensional vector field with components p, q, and r, and they can depend on x, y, and z, well, the curl is measuring the instantaneous rotation of that vector field, and it's doing it, in relation to this axis determined by the direction of the curl vector. Okay, so the direction of the curl is the axis of rotation, and this is determined by the right-hand rule, which I'm going to say a little bit more about as we go through question 6. Okay, but the curl here is it's determining the axis of rotation, and the magnitude of the curl vector, it turns out to be twice the angular speed of rotation of our vector field f. I'm not going to go into much detail as to why it is twice the angular speed as opposed to just the angular speed itself, but in question 6 we will see a calculation that at least helps enforce why it should be twice. Kind of the rough idea is that you'll notice there's two terms here in each component in the calculation of the curl. And so it turns out through an averaging, okay, of these things, you wind up getting this factor of 2. Okay, but in any event, let's go ahead now and look at question 6. This is just going to help us build a little more intuition for each of the statements I'm just have made about the curl vector. So here we're going to be looking at rotation fields. And so we looked at rotation fields in section 15.1 just in the xy plane. So here in three dimensions, we'll be looking at rotation about some fixed axis. Okay, so we're going to let r be the position vector for the point x, y, z in R3. So it's just xi plus yj plus zk. And we're going to let a be a non-zero constant vector in R3. And we're going to define what we'll call the rotation field F to be the cross product of this fixed vector A with the position vector R. And as we're going to show in this problem, okay, the vector field F here in blue is describing rotation about this axis that's determined by this vector A. All right. So to start here, I've gone ahead and just computed the vector field F in component form. So I've just taken the components of the constant vector A and the components of the position vector R and taking the cross product. So we get this right here. And so now looking at question A, it says, if the vector A is 0, 0, 1, find the vector field F and the curl of that vector field. And then what do you notice? Well, if A is equal to 0, 0, 1, it's really just the basis vector k, right? It's just pointing in the direction of the positive z-axis. And to find f, well, I'm just going to set a1 and a2 to be 0 and a3 to be 1. So that's going to give us what? Negative y, it's going to give us an x, and then this is going to be 0. Okay, so here's what we get. If A is 0, 0, 1, then the vector field F is just minus y, comma x, comma 0. And ignoring the k component here for the moment, this vector field minus y, comma x in the xy plane is just the rotation field that we defined in section 15.1. Okay, and this makes sense based on what we're saying this vector field F is doing more generally, right? So here it's just describing rotation about the k-axis, right, in the xy plane. Right, now the curl of this vector field, I've gone ahead and computed it here, is 0, 0, 2. And so notice that the curl points in the direction of this vector A, right, which is the axis of rotation. So as we said in the last slide, the curl points in the direction of uh, the axis of rotation. So that makes sense. And we had actually computed the 2D curl of the rotation field in section 15.4, and we got 2 there. And what that's telling us here is just that the vector field F, it rotates with constant angular velocity, and that omega value, omega is commonly used by physicists here for angular speed, and this is just would be 1 in this case. But in any event, that's just telling us that the amount of rotation there is constant, okay, and we're rotating about the z-axis, right? Just the k-axis there. Okay, so that all makes sense. So now what we want to look at, right, is a more general axis. All right, so pull up the next part. This is B. This says, more generally, use the right-hand rule to explain why the vector field F describes rotation about the axis defined by A in a counterclockwise direction when looking along the length of A from head to tail. So if I'm looking towards the origin, I'm going to see counterclockwise rotation for our vector field F. Okay, well, the main idea here is that, A, this is a fixed vector. And if I think about, say, a point here at the tip of the green position vector, R, okay, then if I'm going to form the cross product of A and R, okay, remember the direction of this cross product is determined by the right-hand rule. Okay, so you have to imagine placing your right hand, right, the base of your right hand along the vector A, and then you curl towards R, and then you look to see the direction of your thumb. It would help if I could have my thumb here in the image to make this a little more vivid. But in this case, the way I've positioned the vectors, F here is going to point in this direction here. And the cross product vector F is perpendicular to both of these vectors, A and R. Okay, so another way to say that is that F is perpendicular to the plane that is spanned by A and R. All right, so now what you want to think about doing is taking the position vector r, let's for the moment think about its length is fixed, and now let's rotate it about this red vector a. So we're going to form this circle, okay, with the tips of all these various position vectors, and for each point along that circle, we're going to get one of these blue vectors, f. Okay, and at every one of those points, right, F is going to be perpendicular to the plane that's spanned by A and R. Okay, so if you think about that, what we're really seeing there is really just the rotation field, much as what we described in section 15.1, but we're just now describing, right, rotation along this more general red axis. Okay, so as we move along this circle here, these blue vectors are going to be tangent to that circle, okay, at each point. All right, so with that in mind, let's now look at C. Okay, let's compute the curl and the magnitude of the curl, okay, for this more general vector field. All right, or actually here, real quick, before we do that, let me pull up this image here. I think this is kind of a nice way to help visualize some of this stuff. So right now I have the vector A is just set to be 0, 0, 1. So this is what we had in part A. And so here's the vector field in that case. And see, it's really just our our 2D rotation field that we defined in 15.1, but now we're extending it in the 3 dimensions, right? So the K component is just constant 0. So you can basically think, we're just taking that rotation field in the XY plane and then, just translating it in a parallel fashion along the z-axis. But you can see, yeah, these things are all rotating, in a counterclockwise fashion. If I look towards the origin, right, because A here is pointing just along the positive z-axis, so they're all rotating about that axis. See, now if I mess now with, say, the various A's, so this gives me, right, a more general axis now, like this. All right, so if I put that vector field in, okay, a little bit crazy, right, in terms of the field, but yeah, right, I can see that these things are all swirling around that axis of rotation. So that makes sense, right? Kind of fun to play around with as you change the axis, and vectors get kind of crazy, but yeah, there you go. It's doing what we are saying it should do. Okay, cool. So yeah, now let's go ahead and compute the curl. So that's pretty straightforward calculation. You just put the components there, computed up here into this cross product, and you wind up doing this, and you wind up getting, well, 2 times the vector A. So in this picture here, here's the vector A. The curl, as we said at the very beginning, right, that is in the direction of the axis of rotation. Okay, so that makes sense. And its magnitude is twice the length of this vector A. Okay, so as I also said, right, the magnitude of the curl is twice the angular speed of the vector field F as it rotates around this axis. And for those of you that have seen something like this in physics, when I write F is equal to A cross R, right, if I think about F as describing a velocity field, right, you could write this as V equals omega cross R, where V here is the linear velocity of, say, your particle that's rotating around this axis, and omega is what we call the angular velocity vector, okay? And its magnitude, which you see here is, if A is playing the role of omega, the magnitude there is just scalar omega, and that's describing the angular speed of the particle as it rotates around the axis. So it's really all the same stuff there. Okay, great. And now for the very last part, this is asking us to compute the divergence of this rotation field. And to do that, well, take the x derivative of the I component. That's 0 because there's no x in there. Then take the y derivative of the j component. Well, that's also 0 because there's no y in there. And then the z derivative of the k component, well, that's 0 because there's no z in there, right? So the divergence of this rotation field is 0, right? So I note here that general rotation fields about a fixed axis are source free, okay? And if you give that some thought, well, the one thing to keep in mind, right, if I draw, say, like a little ball about a point here, is that you're going to have if I think about fluid flow, you're going to have fluid flowing into the ball, so there's going to be inward flux, but then you're going to have fluid flowing out of the ball. Okay, so if I draw a little picture here, here's, say, a little ball here, and I'm going to have fluid flowing in, and then I'm going to have fluid flowing out, right? And the magnitude of the vector F here, right? If I think about fixing my position vector, so I move along, say, one of these little circles here, right? Then along one of these little circles, right, these blue vectors will have constant magnitude. And so they're going to be contributing, well, some inward flux and some outward flux, but these are going to counterbalance each other, giving you a net flux of 0. And there's going to be this symmetry as you move radially outward, right? Because the magnitude's going to decrease the further you are away, or sorry, increase the further you are away from the origin. But again, the contributions are going to be equal and opposite. So you're going to get that net flux of 0. So it makes sense that the divergence for this rotation field is 0. Cool. All right, well, that's going to do it for this question. I'll see you in the next video. Thanks.